exponential growth and decay. In this section, we'll introduce the concept of exponential growth and decay from the calculus point of view by modeling with a differential equation, solving using calculus techniques, and then we'll see some applications of that model. In many natural phenomena, quantities grow or decay at a rate proportional to their size. So for example, if we let P of t represent a population size, and we suppose that that population is growing at a rate proportional to its size, we want to find a function p that models the situation. So since the population p is growing at a rate proportional to its size, that means that we can introduce a differential equation of the form dp dt is equal to kp. dp dt, the rate of change of the population with respect to time, equals kp. It's proportional to its size. It's proportional to the population. Now this is a differential equation. We're not going into a full explanation of differential equations, but this is what is called a separable differential equation, because I can get all of the factors of p on one side of the equation and all of the factors that don't involve p on the other side of the equation. So everything that's dependent, in this case p, I can bring to one side of the equation, and everything that's independent, everything in terms of t, is on the other side of the equation. So in fact, I can write this as 1 over p dp is equal to k dt. And now, since I've now separated this equation, I can now integrate both sides of the equation. So I can write the integral of 1 over p dp is equal to the integral of k dt. And now I'm just using basic calculus techniques. The integral of 1 over p dp is the natural log of the absolute value of p plus a constant. I'll call this c1. The right-hand side, the integral of k with respect to t is kt plus a constant, and I'll call this c2. So now those two constants, they're not necessarily the same, but they are constants. And so if I subtract c1 from both sides, I can just write a plus c on the other side. c2 minus c1 is just some number, some constant. And now if we make the assumption that the population is positive, usually a reasonable assumption, then I can just write this as natural log p equals kt plus c. So now let's solve for p. I'll exponentiate both sides of the equation with the base e, since we have the natural log. And so then I can write that p is equal to e to the kt plus c. And now, using a property of algebra, we may recall that if we're adding in the exponent, that's the same as multiplying with that same base. So I can write this as e to the kt times e to the c. Now, e is a constant, c is a constant, and so what we can do is we can just think of this as a constant. So this is a constant value. And so what we normally do, what's sort of standard is we take that constant and we'll write it in front. So I'll call this big C e to the kt. And if we remember a little bit about algebra, we know that that constant is actually the initial value. In this case, the population at time 0. And so we often write this as P of t is equal to P0 e to the kt. And so what we have now is something that you probably saw in a college algebra course that you called exponential growth. And what we've seen is that we have growth for k positive, and we have decay for k negative. So here's an example. A common inhabitant of human intestines is the bacterium E. coli. Suppose that the population of bacteria grows at a rate proportional to its size, and an initial population of 60 cells grows to 120 cells in 20 minutes. We're asked to find an expression for the number of cells after t hours. Alright, so if we lock into that phrase that the bacteria grows at a rate proportional to its size, what that means is we can use an exponential growth model because of what we just saw in the previous slide. So if we're asked to find an expression for the number of cells after t hours, let's be careful here, t hours. So then what we can start by saying is that the population is equal to the initial population, 60, times e to the kt. Now, we know that the population grows to 120 cells after 20 minutes. So recall that 20 minutes is the same as 1/3 of an hour. Alright, since we have to have our t in terms of hours, we need to remember that. So what we now know is that p of 1/3 is equal to 120. So, substituting into our model, the population after 1/3 of an hour is 120, and so that's equal to 60 times e to the k times 1/3. So now let's solve for k. Dividing through by 60, 2 is equal to e to the k times 1/3. Applying the natural log to both sides of the equation, the natural log of 2 is equal to 1/3 of k. And then multiplying by 3, then k is equal to 3 times the natural log of 2, and using a little bit of our properties of logarithms, we could write that as the natural log of 8, because that's the natural log of 2 cubed, and so k is equal to the natural log of 8. So I'll leave that as in an exact form, and so then our population, p of t, is equal to 60 e to the natural log 8 t. Find the relative growth rate. Now you may not have seen this terminology before. The relative growth rate is the rate of growth with respect to the population, right, to the size. The rate of growth with respect to size. Well, wait a second. The rate of growth, that's dp dt. That's the rate of growth with respect to size over p. Well, wait a second. That's 1 over p times dp dt. Now, if we sort of remember what we started with in the previous slide, what we've seen is that that differential equation that we started with was dp dt is equal to kp. And so if I rewrite that a little bit, if I multiply through by 1 over p, that's the same as 1 over p times dp dt is equal to k. So the 1 over p dp dt is the relative growth rate, is k. So the relative growth rate, k, is natural log 8. Find the number of cells after 8 hours. All right, this is a simple substitution into our function. And so then we would have p of 8 is equal to 60 e to the natural log of 8 times 8. And this is definitely a calculator exercise. And I calculated this as a fairly large number. So let's see, this is 1,006,632,960. So this is a fairly large number. Maybe a scientific notation might be appropriate here when talking about this sort of a number. So let's see, the decimal, we've moved 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So this is approximately 1.007 times 10 to the 9th. So after 8 hours, that's what, 1 billion cells. So fairly impressive. Find the rate of growth after 8 hours. All right, so the rate of growth, that's just dp dt evaluated at t equals 8. Now again, remember from our differential equation that dp dt is equal to kp. So dp dt evaluated at t equals 8 is the same as k times the population evaluated at t equals 8. Now k we've seen is natural log 8. And the population at t equals 8 we answered in the previous exercise, and that was 1.007 times 10 to the 9th power. And so if we multiply that out, I get about 2.09 times 10 to the 9th. And the units on this would be then bacteria per hour. You could also find this value by taking the function that you found in part A, calculating its derivative, and letting t equal 8. But I think it's nicer to understand the differential equation and use it appropriately. When will the population reach 20,000 cells? Now, this is an algebra exercise. We have the population model, and so we want it to reach 20,000. So we'll solve. Where's 20,000 equal to 60 e to the natural log 8 t. So we divide through by 60, and so 20,000 over 60 is equal to e to the natural log 8 times t. We'll apply the natural log to both sides. Natural log of 20,000 over 60 is equal to natural log 8 times t. And then to solve for t, we'll divide through by the natural log of 8. And so then we have the natural log of 20,000 over 60 over the natural log of 8 is equal to t. And this is a calculator exercise now, and we approximate it, and we find t is approximately 2.79, and the units on that would be hours. right, so there's an example of exponential growth, writing a model, and using a little bit of calculus with it. So we've seen an application sort of from biology. Now here's an application that we might see in chemistry. We're told that the mass of a radioactive isotope of an element decays at a rate proportional to the mass of the isotope. Then we're told that the radioactive isotope strontium-90 is known to have a half-life of 28 days. So we're told that the mass decays at a rate proportional to the mass. So dm dt is equal to km. Well, then what we've seen is if we solve this differential equation, we'll get that m is equal to m0 e to the kt. And then what we remember is that k must be less than 0 in this situation for the decay model. Now we're told that a sample has a mass of 50 milligrams. A sample has a mass of 50 milligrams initially. Find a formula for the mass remaining after t days. All right, well, we know that we can then start with m of t is equal to 50 e to the kt. Now, we know from the original statement that the isotope is known to have a half-life of 28 days. What that means is that when t is 28, so when t is 28, mass would be half of the initial quantity. Mass would equal 25. So then substituting, we can write then that 25 is equal to 50 e to the k times 28. Dividing through by 50. 25 divided by 50 is 1/2. Amazing. We're talking about a half-life, and we get a half somewhere in the model. Applying the natural log. Natural log of 1/2 is equal to 28k. Divide through by 28, and k is equal to the natural log of 1/2 over 28. Calculating that, I find that to be approximately negative 0.024755. So then putting that together, our model is then that the mass at some time t, where t is in days, is then equal to the initial mass, which is 50, e to the negative 0.024755 t. All right, we're asked to find the mass after 40 days. Well, t in this model is in terms of days, so we just need to find m of 40. And so that would be 50 e to the negative 0.024755 times 40. And we need to calculate that. And I found this to be approximately 18.58, and the units on this would be milligrams. How long does it take the sample to decay to a mass of 2 milligrams? All right, so we will substitute 2 for the output and solve for t, the input. All right, so solving 2 equals 50 e to the negative 0.024755 t. We need to solve for t. First thing we do is divide through by 50. 2 divided by 50 is a nice number. It's 0.04. So 0.04 is equal to e to the, I'm just going to abbreviate kt, natural log both sides. Natural log of 0.04 is then equal to kt, divide through by the k. And so t is then equal to the natural log of 0.04 over negative 0.024755. And we'll calculate that. And my calculator says that that's approximately 130 days. All right, and finally we're asked to sketch the graph of the mass function. All right, so what I'm going to do is I'm going to use the half-life to help me sketch this model. So we know that the initial mass was 10 milligrams. So let's put, let's use this, I'm sorry, the initial mass was 50. So let's use a scale of 10, 20, 30, 40, 50. And so I'll plot a point here at 0, 50, and these are in grams, milligrams, excuse me. And on the t-axis, I'm going to have this in days. And what I'll do is, I'm going to be smart about this, and I'm going to use a scale of 28 days. So 28, 56, 84, 112, 140, etc. And since the half-life is 28 days, my initial value was 50. After 20 days, I would then have 28 days. I would then have 25 milligrams, and then after 56 days, I'd have what, 12.5, and then after 84 days, what, 6.25, and then 3.125, etc. And so we'll get this exponential model curve, which does something like this. And it'll never actually reach 0. Remember, it's what we call, it's asymptotic to m equals 0. It gets very close, but will never actually reach 0. And so we'll end off with another model. It's called Newton's law of cooling. It's something that we might see in chemistry, possibly physics. Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings, provided that this difference is not too large. And we're asked to model this situation. So let's introduce some notation. I'm going to say that we're going to let big T of little t, we're going to let that represent the temperature of the object at some time t. The actual units on that time t are not critical to the problem. As long as we're consistent, then I'll let that t, I'll say that Ts, I'll let Ts represent the temperature of the surroundings. And we're going to assume that that's held constant in this application. All right, so now what Newton's law of cooling says, the rate of cooling, well, that's a change in temperature, isn't it? The rate of cooling of an object is proportional to, so the change in temperature, with respect to time is proportional to, is equal to K times something. The temperature difference I'm subtracting, right, I'm subtracting between the object, t, and its surroundings, t sub s. Here is a model for this situation. It's in the form of a differential equation again. Again, this ends up being what is called a separable differential equation. And in fact, I can rewrite this as 1 over t minus t sub s times dt is equal to k dt. D little t, excuse me. As before, now I've got everything that involves the dependent variable, capital T, on the left, and everything independent, in terms of little t, on the right-hand side. And so now I can integrate both sides with respect to the appropriate differentials. And notice that, remember that Ts, this Ts is a constant, and so that's like integrating 1 over t minus 5. And we make a simple substitution. It doesn't really require too much work here, but I can rewrite this as the natural log of the absolute value of t minus t sub s, again plus a constant, is equal to k little t plus a constant, and like I did before, I'll combine those constants into a single constant. Now let's make the assumption that the temperature of the object starts at a higher temperature than that of the surroundings, and so our object is cooling. And what that implies then is that T minus Ts is positive, so then I really don't need that absolute value bar. And so then, exponentiating both sides like we did before, I can then write that T minus T sub s is equal to constant e to the kt. I used that same trick that I did before. And then I can solve for t, and so then t is equal to Ts plus c e to the kt. And there's our algebraic model for Newton's law of cooling. So we started with a differential equation model. We were able to solve it and come up with an algebraic equation, which is based on the temperature of the surrounding, some constant, and some k value. So now let's see an application. A cup of coffee has temperature 95 degrees centigrade and takes 30 minutes to cool to 61 degrees centigrade in a room with temperature 20 degrees centigrade. We're asked to use Newton's law of cooling to model this situation. Alright, so what we're going to do, first thing I'm going to do is I'm going to say that T is going to represent the time in minutes. It doesn't matter what units we use here as long as we're consistent. I'm going to say it's the time in minutes. Alright, so let's remember from what we've seen in the previous slide, our temperature model is equal to the initial temperature plus some constant e to the kt. The temperature of the surroundings, well, we read that the cup of coffee is put into a room with temperature 20 degrees centigrade, so that means that T sub s is equal to 20. Alright, so I'll start there. I have that my temperature model is equal to 20 plus c e to the kt. We're at a good start. Now, the cup of coffee has temperature 95 degrees centigrade. Our starting temperature is 95, so that means that T of 0 is 95. When the time is 0, the temperature is 95. So then 95 would equal 20 plus c e to the k times 0. So remember, if we raise e to the 0 power, right, if I take e and raise it to the 0 power, that turns to a 1. And so then subtracting 20 from both sides, we find that c is equal to 75. So we can now revise our model. T is equal to 20 plus 75 e to the kt. Then we're told it takes 30 minutes to cool to 61 degrees. So that means that when t is 30, when little t is 30, temperature is 61. So then 61 would be equal to 20 plus 75 e to the k times 30 minutes. So t equals 30. Do a little bit of algebra here. I'm going to subtract the 20 and divide by 75. So then what's that? 41 over 75 is equal to e to the 30k. Apply the natural log to both sides. Natural log of 41 over 75 is equal to 30k. And dividing through by 30, k is equal to the natural log of 41 over 75 divided by 30. We calculate this. I'm going to take it out to 6 decimal places. And so then I find that k is approximately negative 0.020131. And so then my model, revising my model again, now that we have all the information, my algebraic model is t is equal to 20 plus 75 e to the negative 0.020131 little t. Alright, so we used calculus to come up with the algebraic model, and then we used a bunch of algebra to come up with a more revised algebraic model. And now we're going to finally answer something here. It asks us to determine the temperature of the coffee after 1 hour. Okay, now we have to be careful here because we've said that t is the time in minutes, so we have to recall that that's 60 minutes. And so I'll evaluate t of 60, which would then be 20 plus 75 e to the negative 0.020131 by 60. And we run this through a calculator. And my calculator says that that's approximately 42.4 degrees centigrade. That concludes the presentation for this section.